Hello everyone, welcome back to History of Mathematics. I've got a slightly different setup going here than what you're used to. I am currently working from home and will be for the foreseeable future. I am sure your accommodations are a little bit different as well. So we'll all try to do the best we can with the resources that we've got. We are going to be continuing our work through Stuart Hollingdale's book, Makers of Mathematics. We're going to pick up where we left off in chapter 9, and this is going to be about Newton's Principia. So before we get directly into discussion of Newton's Principia, I'd like to discuss a little background, and we need to know a few names here. And one is Copernicus. So Nicholas Copernicus was a Polish researcher in this time period right here, and he is famous for positing what is called the heliocentric theory in a book called On the Revolutions of Celestial Spheres. He actually published that just before he died. And his work actually triggers the modern scientific revolution. And his work also influenced Galileo. Now, another name that we'll need to know is Kepler. So we've got Copernicus, we've got Kepler. Now, Kepler essentially refines the work that Copernicus did. So Copernicus puts the sun at the center actually of the universe. So Kepler actually makes Copernicus's theory line up with the observed data. Initially, the orbits of planets were thought to be circular because the reasoning behind that went along the lines of, well, the circle is the perfect geometric shape, so since God designed the universe, he would choose the perfect shape, so the orbits must be circles. Well, even when folks had the Earth at the center of the universe, once we started making more accurate astronomical observations, we saw that circles didn't quite work. So people would kind of modify the orbits of these planets so that, okay, the orbit is moving on a circle that rotates on the perimeter of another circle. So by the time Copernicus came around, that business of putting circles on circles had gotten so complicated that he was thinking, well, let's just put the sun at the center to make everything simpler. Now, Kepler actually puts this on firm footing. And he was able to do this because of the work of another person, Tycho Brahe, who I will let you research on your own. Tycho Brahe is, of the three names that we talked about, Copernicus, Kepler, and Brahe, he's by far the most interesting one. But what Brahe did was he had an observatory, and he was a meticulous collector of astronomical data. And when Kepler got access to all this data, he formulates 3 laws of planetary motion. So the first law is this, that the orbit of a planet is an ellipse with the sun at one of the foci. So Kepler is dropping the insistence that the orbits of planets are circles, and he says, okay, I've got access to all this data, and everything works out if I make the orbit an ellipse rather than a circle. And you'll remember from your analytic geometry that an ellipse is the set of all points where the sum of the distances from 2 points called the foci are constant. Okay, so Kepler ditches the circle idea and goes to ellipses. The second law says that the line joining the planet to the sun sweeps out equal areas in equal times, and this third law relates the orbital period to the semi-major axis. So this is a crude drawing of an ellipse right here, but the foci are 2 points in here, such that whatever point I go to on the ellipse, if I take this d1 and d2, d1 plus d2 equals some constant. Okay, that varies depending on the ellipse, but no matter where I go, if I took the distance between these 2 points, foci 1, foci 2, the sum would be constant. So what Kepler's law is saying is that if I look at the time it takes my planet to get from, let's say, here to here. Okay, and if I look at the line segment joining the planet to my one foci where the sun is, if I look at that area, and I don't know, let me go over here. Let's say the planet goes from here to here in the same time as it did to go from here to here. So Kepler's second law is saying that these two areas would be equal as long as the time it takes for this trip is the same as the time it takes for this trip. So that's what Kepler's second law is all about. Now, we kind of need to know that to understand the work of Newton in his Principia. I know it looks like it should be said Principia, but the name, of course, as you can read in Stuart Hollingdale's book, is in Latin. The original name is in Latin, and Latin didn't have a soft C sound. The C was sounded like a K, so that's why I'm pronouncing it that way. Okay, so Newton's Principia, which was researched in 1665. Okay, now, as we know in the last chapter, during this time period, Newton was home from Cambridge because the university was closed due to an outbreak of plague. So, kind of everything old is new again. Now, that was when he researched this work. He didn't actually start publishing it until 1686. And as you can read in the book, people kind of had to poke, prod, and cajole Newton into publishing it, and in particular, Edmund Halley was instrumental in getting this work out there. So the big ideas in Newton's Principia were the fluctuation'el calculus, which is essentially differential calculus, because when Newton is doing this work, he has to deal with quantities that are continually changing. So basically he invented differentiation to deal with that process. And to deal with differentiation, Newton has to figure out a way to deal with limits. And that's what that fluctuation'el calculus is about. It's basically Newton's way of dealing with limits. So that's a huge thing to come out of this work by Newton. And the other thing is that he relates Kepler's second law to the inverse square law for gravitational attraction. So I gotta edit that a little bit. So the inverse square law for gravitational attraction says that the gravitational attraction between any two objects in the universe is the product of a constant, the gravitational constant, times their masses, and it's inversely proportional to the square of the distance between them. So what Newton is able to show is that if this is true, then Kepler's second law, the one about equal areas swept out in equal times, has to be true. So it's really big because Newton's work actually helps us deal with a thing that would probably bug people about Kepler's laws, in that, okay, I get the ellipse thing because it makes the observations line up with what we actually are experiencing, but why should this equal areas and equal time things be true? And Newton says, okay, well, if this simple law for attraction between bodies holds, then Kepler's second law has to be true. So that, among other things, is part of the importance of Newton's Principia.